The standard internal combustion engine is a system bound by the economics of planned obsolescence and deliberate physical limitations. Factory components are built to a good enough threshold, ensuring the machine survives its warranty period rather than reaching its maximum physical endurance. Our objective is to dismantle this consumer-grade framework entirely. We will achieve this by integrating continuous process industrial plant architecture into a baseline consumer engine. The platform for this engineering is the most common vehicle on American roads, the Ford F-150, powered by the 3.5-liter EcoBoost V6. Applying industrial plant logic to this engine allows us to isolate and resolve the specific physical triggers of mechanical failure. The 3.5-liter EcoBoost is a sophisticated assembly of twin turbochargers and direct injection, but it remains vulnerable to three specific vectors of decay. The first is mechanical contamination, where microscopic particles act as an abrasive that slowly destroys internal tolerances. The second is boundary lubrication, the metal-on-metal contact that occurs during dry, cold starts before the oil pump can pressurize the galleries. The third is thermal extremes, which cause asymmetric material expansion and bake stagnant oil into carbon deposits inside the turbochargers. We will replace passive maintenance schedules with active systems governed entirely by fluid physics. Systematically neutralizing these three vectors shifts the mechanical outcome from a predicted failure date to a condition-managed operational lifespan. Mechanical contamination begins with the limits of standard filtration. Most automotive filters allow particles as large as 30 microns to circulate freely through the bearings. To halt this wear, we drop the filtration threshold to an absolute 10-micron mesh. Cutting the particle size in half creates a fluid flow challenge. This formula governs flow resistance. Pressure drop is determined by viscosity and flow rate against media permeability and surface area. A 10-micron mesh reduces permeability, which would cause pressure drop to spike. We compensate by increasing surface area. An oversized canister with deep, sharp pleats maintains flow despite the restriction. We also position rare earth neodymium magnets at the inlet to capture ferrous wear particles before they reach the mesh, extending the surface life of the element. Manipulating these physical variables allows us to achieve microscopic filtration without triggering bypass valves or reducing oil volume. Because a 10-micron filter captures debris more efficiently, it loads faster than a standard element, necessitating more frequent maintenance. To manage this without engine downtime, we utilize a duplex filter manifold, a design common in high-output marine engines. This setup uses two symmetric, redundant filter chambers. One remains active while the other is held in reserve. The transition between these filters presents a mechanical risk known as deadheading the oil pump. If the flow is blocked for even a microsecond, the positive displacement pump will create a pressure spike that can rupture engine seals. We use a make-before-break open center valve. This ensures the pathway to the second chamber opens before the first is closed, providing a seamless transition for the oil flow. An automated differential pressure sensor triggers this switch the moment it detects 12 psi of restriction in the active element. This duplex architecture creates a continuous purification loop where maintenance is dictated by physical data rather than a calendar. We must also address the air intake, specifically the silica dust particles under 5 microns that pass through standard paper filters. Inside the cylinders, this microscopic dust mixes with the oil film to create an abrasive slurry. This mixture acts as a grinding paste, slowly wearing down the piston rings and widening the engine's crosshatch tolerances. We eliminate this by installing an industrial-grade cyclonic pre-cleaner, which uses centrifugal force to separate and eject heavy particulate matter before the airstream ever reaches the primary filter media. Removing silica at the intake level halts the primary driver of piston ring erosion and preserves combustion chamber compression for the life of the engine. The final vector is thermal variance. Nearly 80% of mechanical wear is concentrated during the first few seconds of a cold start. Overnight, oil drains into the pan, leaving the engine to start with metal-on-metal contact. We prevent this wear by implementing a hardware interlock protocol that conditions the engine before ignition. First, an integrated block heater brings the aluminum and iron components to thermal equilibrium to ensure uniform expansion. Next, an electric pre-oiler pump forcefully pressurizes the lubrication galleries, coating the crankshaft and cam lopes before they rotate. The ignition remains locked out until the sensors confirm that the pre-oiler has reached target operating pressure. Following a drive, a post-run cooling cycle prevents heat soak, which protects the turbochargers from carbon deposits caused by stagnant baking oil. Preconditioning the engine's temperature and pressure removes the chaotic variables of daily use, maximizing the lifespan of the base materials. While we have eliminated mechanical wear, engine oil still faces chemical degradation. Up to 30% of motor oil consists of chemical additives that are slowly consumed as the engine operates. Liquid contaminants, such as fuel dilution from combustion blow-by, also accumulate over time and cannot be filtered out. Our duplex filter system provides a built-in solution for this by using the offline chamber as a pressurized sampling port. Periodic laboratory analysis of these samples tracks the remaining additive levels and viscosity, providing a precise data point for when the oil must be replaced. Shifting to condition-based data allows high-quality synthetic fluids to safely run for 50,000 miles or more, far beyond traditional estimates. This continuous loop system reveals the staggering amount of waste built into standard maintenance cycles. A typical consumer-grade F-150 driven for 300,000 miles will discard 60 filters and roughly 360 quarts of engine oil. In contrast, the engineered cycle uses 0 disposable filters and requires only 80 quarts of fluid over the same period, an 85% reduction in total oil consumption. Based on the cost of high-quality fluids and parts, this equates to a lifetime savings of over $9,000. This figure does not include the capital saved by preventing turbocharger failures or timing chain wear through superior filtration and pre-lubrication. Aggressively engineering the engine's environment changes its trajectory from a series of inevitable failures into a durable, multi-generational machine.